Okay, it is 10 o'clock. We're going to get started here. All righty. Good morning, everybody. Okay, half of you are awake. Good morning, everybody. All right. Welcome, everybody, to the Humanist Society of Greater Phoenix. My name is Alex Zygmunt. I'm the president of the organization. I wanted to say welcome to you all, and thank you so much for attending this today. We'd like to get started on a few announcements, so we'll go through those real quick. But first, who is here for the very first time? I see a lot of new faces. Welcome. Thank you so much for joining us today. As you see, there's breakfast in the back. Our breakfast crew gets here early in the morning, and they fill us up our bellies so that we can absorb all this wonderful information. Who enjoyed breakfast this morning? Yes? All right. Thank you to our breakfast crew for getting here. I think it was 6:20 when I saw Pete walk through the door. So a lot of this stuff goes through volunteers. Nobody here gets paid. Roger, our treasurer, can affirm that. Although, if you would like to give him money so that we can keep this building up and running, that'd be great too. So we do have a lot of events that happen here in the building. All of it is volunteer-led. All of it is volunteer-run. So if there is an event that you'd like to see here at the community center, please let us know. One of the board members, all of our board members, please raise your hands. Please let one of us know if there's an event that you'd like to see here at the community center, if there's something that we're not representing that you would like to see out there in the community. As you know, we have the Little Free Pantry out front. That's for the school kids that are coming by, families that might need a little extra sustenance. We also have the Little Free Library, which is constantly replenished. We also do philosophy under the influence. We do blood drives. We do the VAST meetings, which is the Volunteer Mutual Aid and Solidarity Team. So we work alongside all kinds of different organizations. One of the most prominent has been the ASU's Project Humanities. If you're not familiar with that, it's a fantastic organization. Dr. Neil Lester has spoken here in the community center before. And we just recently, during the last board meeting last month, decided to donate to become founder members for ASU's Project Humanities. So we are now listed through ASU. So, yes, exciting times. A number of things that are going to be happening here over the next few weeks is we're going to be kind of refreshing the room a little bit. Part of that is the AV system. That closet is going to be torn out, rebuilt, and then more AV stuff is coming in. Some is going away. Yes. Oh my goodness. So, but we're working on it. It's all due to small donations, whether or not you help out today or even hop up on our Patreon channel. That helps go towards the AV system as well. So, $5 a month would help with those types of contributions and going from there. So, again, if there's something you want to see, please let us know. We'll get you up and running. But what I wanted to mention today is something that's very, very important to me, and I'm very glad to announce that, as you see here, a new humanist group has started here in the Phoenix Valley. So, I want to help them as much as I possibly can. The individual who is running it is, I met her years ago during what was then known as HSGP's West Valley Initiative. This was right before the pandemic. We started working with people in the West Valley to see if there was something that we could do to help them get something running over there. The pandemic hit. We ran out of resources. We ran out of time. But and unfortunately, that initiative kind of fell to the wayside. But Audrey here, as you see, started a new group that is going to be serving the Northwest Valley. So if you are online watching this and are in the Northwest Valley and you're like, Mesa is way too far, I'm not making that drive, I don't blame you whatsoever, because with my work, I do a lot of driving, so I get it. But please join them. Please volunteer with them. Please donate. One of the things that Michelle mentioned earlier is that through our Meetup account, we can have up to 3 different types of pages. I'm considering donating one of the 3 pages that we have so that they can utilize it for their own group at no charge to them, because I want them to succeed. We need more humanist groups, not less. Humanism is something that is desperately needed in these times. So if you're interested in helping with that group, if you live in the West Valley, North Valley, please considering helping out with that as well. And at that point, we're going to begin the process of introducing our speaker.
Northwest Phoenix Humanists. No meeting place just yet. Hello, everybody. How's everybody doing this morning? I'm Aaron Leitz, our Vice President here at HSGP. I'm very excited to have our speaker with us today, Dr. Blitz. Samuel Blitz, known as Dr. Blitz online, is a mathematician and physicist specializing in relativity and geometry. Since earning his PhD in mathematical physics in 2022, he's taken to the public arena, engaging in science outreach, as well as philosophical and political debate and discussion. He's authored or co-authored more than a dozen scientific papers in prestigious journals, focusing on Einstein's general relativity and its implications for black holes and cosmology. His academic influence is marked by international speaking engagements and research grants that support his continued investigations into theoretical physics. Begun as a whimsical endeavor to dissuade flat earthers and educate the broader public about deeper physics, Dr. Blitz's social media following has grown since 2022 to more than 400,000 followers on TikTok and 20,000 subscribers on YouTube. He creates daily educational content demystifying physics and debunking pseudoscience. Dr. Blitz's passion for science communication and expertise in his field makes him a potent debate opponent and inspiring teacher. Being able to do both, educate and research, means that, in his view, he is living the dream. It is my pleasure. Please welcome Dr. Blitz.
So that was lovely. I wrote most of it, so, you know, of course I'm going to say nice things about myself. I know that some of the talks, some of the Sunday speakers are a lot more philosophical or sociological. I want to talk about black holes, because I think black holes are cool, and I think that you guys should too. Just as a quick warning, we are talking about black holes here, so there might be some math. If you're not into that, just close your eyes, plug your ears, and then a few slides later, we'll be back to talking about like the cool pictures and stuff, right? Right. So, title, totally reasonable thing. So this is me when I was 4 years old, 4 years old, right? So apparently, these are fake glasses, by the way, right? There's no lenses in them. But apparently, even going back as far as, when I was a 3 or 4 year old, I was really, really interested in science. So much so that you might call it a love story, if you will. There's, I guess, fake test tubes there. I don't know what the blue thing is necessarily. It's something. I also was apparently really into Batman. Not so much anymore, but I was at the time. But I am still interested in science, right? And so that interest in science stayed with me for a long time. It stayed with me, till now, I guess. But by the time I was 8 or 9, I had been toying with different sciences, right? I had thought about marine biology. I have a distinct memory of drawing undersea fish. The viperfish is still one of my favorites. I had toyed with geology, with meteorology, the various ologies that you run into when you're a 7-year-old, I guess. But by the time I was 8 or 9, I was hanging out with a good friend of mine who, I have since lost contact with. And we were just scrolling around on Google Images, as you do as an 8 or 9-year-old. It had just come out. And we stumbled upon a picture like this, some CGI rendering of a black hole. And it was then that the two of us decided we're going to do that for the rest of our lives, right? Turns out he didn't, but I did. So there's a whole journey there. I'll explain to you how we ended up where we ended up. But over the next few years, 10, 11, 12, as a tween and then as a young teenager, I started just reading a lot, right? I read A Brief History of Time by Stephen Hawking. If you haven't read it, it's probably one of the greatest pieces of modern science communication in history, I think. I read The Elegant Universe by Brian Greene, who's a string theorist, not quite related to black holes, but it's all tangentially related anyway. I read Hyperspace by Michio Kaku. You probably know and have heard of Michio Kaku before. I watched a lot of these documentaries that you have on PBS, this kind of thing. There was a show called Nova. I don't know if you guys are familiar with that. There was a special on string theory back in the early 2000s, and I watched that. I thought it was amazing. Later, when I was a teenager, I read Death by Black Hole by Neil deGrasse Tyson. I guess he wasn't as popular when I was a young person, but, well, a younger person anyway. And in the background of all of this, in the background of reading about these cool physics ideas, I was also really enamored with Albert Einstein. I mean, like, the guy's name is synonymous with genius, and I was like a smart kid growing up, right? So I'm like, that's me. It wasn't. But but the story was still fascinating, and because you have these black holes, which I knew somehow were related to Albert Einstein, and then you have this like super genius guy. I was enamored by like his life story first, and then also by the stuff that he was doing. And it turns out you don't need much more than algebra to do, or at least think about, some of the things that he was talking about 120 years ago. And so I was just writing down equations that Einstein wrote down, copying them off the internet, of course. And I was fascinated by like how you can calculate how clocks tick at different rates, all of this stuff. So this is me as a teenager, and really, by the time I was in high school, I had my life planned out, right? I would go to university, I would get a double major in math and physics, because that's what you have to do if you want to be a theoretical physicist. Then I would go to grad school, I would study black holes there, then I would go work as a professor and be teaching about black holes. The whole thing was planned out. I did eventually graduate. This is a picture from 3 years ago. This is a friend of mine. That's my supervisor. That's me, if you can't tell. I did end up doing the double major. I did end up getting my PhD. I wasn't studying black holes, but something tangentially related. Still not a professor, but that's pretty normal, especially in this day and age. And now, the research that I do is a bit broader than just black holes, but I still like black holes a lot, so much so that in the last year and a half, I published 3 papers about them. This one's still under peer review. The other 2 are currently in print. And I'm still working, even though I'm not affiliated with the university. This is still an area of interest for me, as it has been for 25 years, I guess, at this point. But I'm not at a university, so if anybody works at a university and wants to hire me, you should let me know. So that's how I got where I am. Still love black holes. My interests are a little bit broader now. But now my job is going to be to convince you that you should like black holes too. So the first thing about them that I think everybody, if you've ever seen a PBS special about black holes, which probably 5% of the people in this room have, you'll have seen pictures like this, right? And they're just really fascinating looking things. Of course, this is a CGI rendering. We don't have pictures of black holes like that, at least not exactly like that. But there's something about them, something about these artist renders that are just really cool and fascinating and curious, and they're these strange space objects, and I don't know how else to put it except just to tell you, just look at the thing. How can you not be interested, right? And perhaps there are a few reasons why you might think that they're interesting that I could think of. In some sense, they're kind of the most extreme things in the universe, right? So I put just a few here. Black holes are the densest things in the universe, the densest things that anybody knows about. As far as we can tell, there's nothing denser. In fact, this little rendering here is what it would look like if you took away all of the distortion, if you plopped a black hole that has the mass of the sun next to Vancouver. So this is something that's 6 kilometers across. For those who don't speak metric, it's like 4 miles across or something like that. And it weighs as much as the sun does, which is crazy. They also have the most extreme gravity in the universe. You might think that, after a long workout, your legs feel tired and you feel very heavy. And then if you were to go stand on some super dense planet orbiting some distant star, you might feel twice as heavy because the gravity is twice as strong. And if you were to go stand on a neutron star, another extreme object, you might feel 1,000,000 times heavier. If you were to somehow stand at the edge of a black hole, this little, on this black sphere, you would feel infinitely times heavier. You can't get any more dense and any stronger gravity than that. So that's kind of weird. I don't even know what that means, but it's true. You can do the math, and that's what would happen. They also, as the name implies, are the darkest things in the universe, right? A black hole is a black hole because light goes in and it doesn't come out. The way that we see things is, typically, you shine a light on something, and then it bounces back and comes to you and lands in your eyeball. Or sometimes, if the things are very hot, like the sun, it will emit its own light. Black holes do neither, with a big asterisk there, by the way. So they're the darkest things in the universe. You can't see through them. They're also, strangely enough, the smoothest things in the universe, if you understand what I mean by smooth. And what I mean by that is the surface of a black hole isn't a surface like a planet is, right? It is more of just a place, and there's an inside the place and an outside the place. But if you were to somehow draw an imaginary boundary around the inside and the outside, it would be perfectly spherical, as long as you wait long enough, or perhaps ellipsoidal. But the point is it wouldn't have any jagged edges at all. There would be no mountains on a black hole. There would be no valleys. It would be as smooth as you could possibly get, which is kind of surprising if you think about it, because these are very, very chaotic objects. Also, for the same reason, even though they're not physical objects, per se, if you were to figure out how fast it should be spinning, if they could spin, which they do, you would find that they spin at near the speed of light, which, you know, as we all hopefully know, the speed of light is kind of the upper speed limit. You can't go faster than that. So they are, in some sense, the fastest things in the universe, too. And then, most bewildering of all, they're also the brightest objects in the universe. I said they were the darkest. They're also the brightest. They're objects called quasars. Quasars are objects deep, deep in space, billions of light years away. And they're basically what happens if you have a black hole that's currently eating tons of stuff and is making that stuff glow so hot that we can see it from a billion light years away. And they really are the brightest things in the universe. And it's powered by a black hole. So clearly, they are very extreme things. So that's one reason you should care about them. Another reason you should care about them is that they're weird. It's not just that they're extreme, they're weird, right? So the famous thing about black holes is that they have this point of no return. It's called the event horizon. It's this thing in the top left-hand corner. The name is for historical reasons, but if you go in, that's fine, you can go in. You might have a bad time, but you can do it. But you can't come out. And so, why not? Well, the strangest feature of a black hole, in my opinion, is that the whole reason you can't come out is because there's just no out anymore. The space around a black hole warps so much that the outward direction that you would like to go in to leave is pointing inward now. And it's so weird to think about because we usually think that you can move in any direction you want. Not around a black hole you can't. There's only one way, and it's inward. And then, of course, maybe you've heard about, in science fiction or something like this, maybe you've heard about like time warps in Interstellar, of course, if anybody's seen that movie. One of the characters hangs out near this black hole planet, and then they come back and the guy in the spaceship has aged like 30 years. That's real. That's a real thing. If you hang out near the edge of a black hole, near the event horizon, your clock on your wrist, if you're wearing a watch, I guess, might only tick a few minutes, and it might be hundreds of years for someone that's far away. And that's weird. Another reason why black holes are just so, they're crazy, right? And then, of course, there's the most enigmatic part of a black hole, which is the singularity. Now, who knows if these things actually exist? We've certainly never seen one. But the singularity is, in some sense, supposed to be a point of infinite density at the center of the thing. The black hole we usually think of as the whole region that's encompassing the singularity. It's the region inside the event horizon, but the singularity is really the idea of where the mass actually is, where the heavy stuff is. And if you work out the details of what the geometry of space-time is doing at the singularity, well, it just stops existing. And that's weird. Usually we think that if you go somewhere, even if you're stuck there, your wristwatch will still tick forward. You'll still experience time even if you're stuck somewhere. Like if somebody boxed me in, I couldn't move, but at least my watch would keep going. If you get to the singularity, if you could somehow survive it, which of course you couldn't, your watch would stop ticking too. You would essentially cease to exist. Now, we don't really have a good reason to think that such a thing is possible, but that's what the math says. And so it's the goal of people like me, and hopefully maybe other colleagues and perhaps maybe people in the audience, if they find it interesting enough, to figure out what's going on here. And then also what's going on here, and what's going on everywhere. It's all very weird. And that's what we use math for. So hopefully, if you didn't care, you'll at least have a little bit of an appetite for what I'm about to tell you, because what I told you was what got the kinds of things that got me interested, but there's so much more than that that is worth talking about. There's a lot of history. This idea goes back hundreds of years. There's a lot of theory. I'm a theorist. That's my forte. There's also like observations, which is a new thing. We can actually see these things now. And so in the coming, 25 minutes or something like this, I'm going to go over basically history, theory, observation, and there will be a little bit of math in there, I promise. It won't be so bad. Maybe some algebra. I'm not going to make you do it. There won't be any quizzes. But just to show you how some of these features come out of the theory that was kind of described more than 100 years ago, it's worth at least showing you what it looks like. So let's get started with the history. So we start with Isaac Newton in 1687, right? Isaac Newton, he's kind of the father of modern physics. He didn't invent gravity, but he may as well have. Prior to Isaac Newton, I guess Galileo Galilei observed that everything falls at the same rate. He did an experiment on the Tower of Pisa, but no one really knew how it worked. Nobody understood that the things that are happening in the sky was the things that were happening on Earth. Isaac Newton, of course, he did that during a pandemic, I should say, during the Black Plague, if I remember correctly, which means that he spent his years in quarantine a little bit better than I did. But needless to say, we have him to thank for this idea of gravity existing at all. He wrote down the so-called universal law of gravitation. Every mass attracts every other mass, blah, blah, blah. And one of the consequences of the formulas that he wrote down, because he was a mathematician, is that if you were to try to jump off the Earth, well, if you jump just a little bit, you won't go very high. If you jump faster, you'll go higher. And if you jump even faster still, you might eventually leave the Earth entirely. This is what's called escape velocity. And you may have heard about this in rocket science too. You basically need to make your rocket go fast enough to leave Earth. Now, most rockets, satellites, end up orbiting the Earth. But if you really want to leave, you have to go, 11 kilometers per second or something like this to leave the Earth. And so this idea of escape velocity existed. Isaac Newton kind of came up with it, or at least he wrote down the mathematics that made it possible. And then about 100 years later, this fellow, John Mitchell, by the way, this guy is Isaac Newton. This guy is John Mitchell. Michel? I don't know how to say his name. But anyway, about 100 years later, John Mitchell, he thought, well, light has a speed, right? At the time, they roughly knew how fast light was going. And so maybe if the escape velocity of something was high enough, light could get stuck. And so we named these things dark stars. The idea of a dark star is it's exactly as it sounds. It's a big, heavy thing in space like a star, but it's dark, just because the gravity is so strong, the light can't escape. A few years later, I guess 13 years later, we have another, perhaps more famous mathematician and physicist, Pierre-Simon Laplace, more famous than John Mitchell. Everybody knows Isaac Newton. So we have Laplace over here, who basically came to the same conclusion, I suspect independently from John Mitchell, basically concluding that if you took something that is 250 times bigger than the sun and about the same density as the Earth, well, then light wouldn't be able to leave it. And so he said, well, maybe these things exist out there in the universe, we just can't see them because they're dark. But historically, there was this fight over whether light was a wave or a particle. Isaac Newton was a proponent that light was a particle. And so it makes sense that, a particle, like a little, think of baseball, it could get pulled back by gravity. But other people at the time, like Thomas Young, were putting forward this idea that light was a wave. And nobody really knew how to make sense of a wave getting stuck by gravity. And that was becoming the dominant position amongst early physicists, that light is definitely a wave. And so this idea of a dark star, something that can pull light back towards it, kind of just faded into obscurity for over 100 years. It wasn't until the GOAT himself, Albert Einstein, came along that we have to thank for bringing this idea back. Actually, it wasn't him, it was somebody later. But we have to talk about Albert Einstein, because if it weren't for him, we wouldn't have black holes, right? So if you guys don't know why Albert Einstein is famous, you should, because And, I say this a lot. People are always surprised. They'll be like, who's the most underrated physicist of all time? It's Albert Einstein. Albert Einstein's the most underrated. And that comes as a shock to people because everybody knows who Albert Einstein is, and he's probably the most famous physicist who ever existed, and yet he's underrated because he basically is the person who is responsible for creating all of modern physics, all of it. So let me just tell you about his 26th year on this planet, 1905. So he was 26 years old at the time. It's the so-called Annus Mirabilis, means something like miracle year in Latin. And the reason it's called that is because he wrote 4 groundbreaking papers in 1905. Briefly going to sketch what those are, just so you can know how underrated he is. In 1905, the first paper he wrote was giving a theoretical description of the photoelectric effect. Now, this isn't super well known about, but basically, this is a phenomenon that physicists 20 years earlier had observed happens when you shine ultraviolet light on a metal. For some reason, electrons just kind of pop out of it. Nobody knew why. And he gave a theoretical explanation for this. In fact, this is what he won his Nobel Prize for 17 years later. And the reason why this result is important is because it provided the foundation for showing that quantum mechanics was real. So keep in mind, Einstein's first thing was quantum mechanics, providing the foundation for that. So that's a big deal. The second thing he did was he gave a theoretical explanation for Brownian motion. Brownian motion is this idea that if you kind of drop pollen in water and you zoom in on it with a microscope, it'll jiggle. Nobody knew why. He came up with a theoretical explanation, basically saying, well, if atoms are real, that would explain why. So in this second paper, he proved the existence of atoms. His third paper was the paper on special relativity. This is where he assumed that the speed of light moved at a constant rate, and you get all these weird things about, time, clocks moving at different rates for different people, very, very weird stuff. And then in his fourth paper, in 1 year, he wrote down the paper with E equals mc squared in it, now the most famous equation in history, and also led to nuclear power. So that's 1 year as a 26-year-old working at a Swiss patent office. And he didn't get a professorship, so what chance do I have, right? So it turns out that it's actually only the third of these, the special relativity paper, that will be relevant at all. But this just says why, they call it the Annus Mirabilis for a reason. And then, he wasn't done. 10 years later, he comes up and he he dethrones Isaac Newton as the king of gravity with his theory of general relativity. Now, I should say, he didn't do all of this on his own. Obviously, there were a lot of other people working at the same time on similar things, but these were all his significant contributions. Anyway, he came up with general relativity not to talk about black holes. That wasn't the goal. It was essentially because there was some weird stuff going on with special relativity that he needed to make sense of. General relativity comes from special relativity. And there was also this weird observation about Mercury's orbit around the sun that nobody had been able to explain for 100 years. It just didn't exactly match what Newton said it should. And Newton's universal law of gravitation was supposed to be the end of the story on gravity. So his new theory could explain Mercury's orbit. The cost is that he had to come up with this idea of spacetime that was bending and warping, which is a huge paradigm-shifting idea. So this is the key, this general relativity business. This is how we get to black holes. And so I'm going to have a brief slide, or a brief set of slides, where we go into what spacetime is, because that's kind of critical, what it means for it to bend, what the whole deal is with relativity. Then we'll get back to the history. So there's an important question of what is spacetime. It's kind of in the name, right? So space is how we measure distances. Time is how we measure durations. You might say spacetime is how we measure both of them. And that's roughly true. And even before Einstein came up with his general theory of relativity, in his special relativity, he had this idea that the laws of physics should be the same regardless of who's measuring them, right? If you're a theoretical physicist or an experimental physicist and you're, flying through space at 1,000,000 miles an hour, you should come to the same conclusions that I should here on Earth. It's a really not that, it's not that surprising. We would kind of expect that to be the case. But this statement has huge implications about the nature of spacetime, right? Because one of the ideas of Maxwell, this is another theoretical physicist in the late 1800s, is that you can actually figure out the speed of light from just the laws of physics, right? The light speed is related to, various properties of electricity and magnetism. And so if the laws of physics are the same to everybody, that means that everybody should have the same speed of light. And that's really weird, because if you've ever thought about, say, throwing a baseball on a train, if you throw the baseball at 20 miles an hour while you're on the train, and somebody's standing off to the side, watching, on the ground, not on the train is moving at 50 miles an hour, 50 miles an hour north, and no. If the train's moving at 50 miles an hour, you throw a baseball 20 miles an hour, somebody on the side might see it moving 70. 50 plus 20 is 70. But then, what Einstein seems to be saying is that if you shine a flashlight while you're on a train, you'll measure 300,000 kilometers per second, and somebody on the side of the train will also measure the same amount. And that's weird, because speed is distance over time. And so if somehow two people moving at different speeds are measuring the same speed, something weird must be happening, right? There's some strange implication that different observers have to measure durations, time, and measure distances, space, in different ways, meaning that the second hand on your watch should tick at a different rate depending on how fast you're moving. And one of the implications that was a clever observation by, I believe it was a man named Poincaré, is that if you take the predictions of how they should change, so you always get the same speed of light when you measure it, it looks eerily like what you would expect to happen if you were to somehow rotate space into time and vice versa. And so that means that space and time, usually we think of rotating things, right? That's a space thing, but if you can rotate space into time, then maybe space and time are just two sides of the same coin, and you end up with this thing that we now call spacetime. Now, what does the next bit say? Oh yeah, I'll talk about that in a minute. So this is the idea that comes from special relativity and from a few other scientists earlier, that we have this joint object. We have 3 dimensions of space, 1 dimension of time. We call it all spacetime. And now space and time can kind of interchange with each other. So that's the first step to understanding what's going on with black holes. And as an aside, Newton's first law is an object in motion stays in motion, an object at rest stays at rest unless an external force acts upon it. It's probably triggering some PTSD from high school or something. There's actually a neat way to understand that from the space-time point of view. It's just that things travel in straight lines in space-time. If there's no force, then you're moving at a constant rate through time, you're moving at a constant rate through space, and that would just be a straight line if you were to plot it on a graph, right? And so we can use this idea that things will travel in a straight line if nothing's happening to them to now think about what happens if the space-time itself is curved. So we have to talk about curvature. We have to talk about these things called geodesics. I'll explain what that is, but here we have a diagram of the surface of the Earth, or the surface of some ball. In our everyday life, we have this idea of what a straight line is, right? On a sheet of paper, you can just get a ruler and draw a straight line, right? I don't really know how else to describe a straight line on a sheet of paper except by just getting a ruler and showing you. So there's actually a deep question of, what does straight actually mean? What is a straight line on a basketball, right? Now you could say, well, there are no straight lines on a basketball, but if you were to talk about straight lines somehow, so that maybe you can talk about things moving in straight lines, like Newton's first law, well, you better come up with a good explanation. And it turns out there's a way to do this. There's actually 2 equivalent ways. One is you can just say a straight line is the path you take when you move without turning. That's a pretty good definition, right? It agrees with what we would see on a sheet of paper. You get in your car, you just start driving, you never touch the wheel. You'll either get in an accident or you'll end up in a straight line. Another possible way to describe such a straight line is taking the shortest path between 2 points. That's a fairly good explanation for a straight line. It actually turns out these 2 things are the same. You can work out mathematically that they have to be identical. If you move without turning, you will end up along the shortest path. And by the way, on the surface of a sphere, this line connecting A and B here, that is the shortest path, and it's called a geodesic. It's called a geodesic, because straight line kind of has some baggage with it. So there's a name for these kind of general versions of straight lines, which are just the shortest paths between points, or moving without turning. And just to connect back to people's experiences, if you've ever flown across the Atlantic, from the United States to Europe, say, which I recognize most people will not have, but if you have, you'll find that on the little flight tracker, you'll swing near the North Pole, and you'll be like, well, how does that make sense? Shouldn't you just fly from Europe direct to LA? But you swing near the North Pole because that is actually the straightest line on the surface of a sphere. It curves, even though it's straight. And so that's why they take that route. And by the way, this is a complete aside, one of the easiest ways to tell a flat earther that they're wrong is to ask them to explain why is it that a flight leaves Sydney, Australia to go to Santiago in Chile. Santiago in Chile or Argentina? It's in Chile, okay. Somewhere in South America. Why does it curve down to Antarctica before swinging back up? And it's because the Earth is a globe, of course. Right, but the point is that these geodesics are actually relevant because the Earth is a sphere. It's curved. So the point is that somehow we can talk about straight lines on curved things in a useful and mathematical way. Now, the way that we talk about the curved things, as I kind of just alluded to, is that there's some relationship between the curvature of the thing and what the geodesics look like, the set of straight lines. If the thing has curvature, then you would expect the straight lines to not look straight. And because the geodesics, these straight lines, are in some sense capturing the shortest path, well, if the way you measure distances changes from place to place, that will affect the shape that these geodesics take, which will then inform on the curvature. So this is all to say, the way that we could talk about curvature, even without looking at a thing, the way that we can talk about curvature is by how the way we measure distances changes from place to place. And I'm going to give you an example relating to the sphere here. There's math. So the way that we talk about the variation in distance measures from place to place is with an object called a metric tensor. You can just think of it as like an array. And basically, the elements of the array tell you how much it costs to move in a particular direction. So this top left-hand one here, you have a 1 there. That's telling you how much it costs to move north-south on a globe. And you'll see that to change your latitude by 1 degree is going to be the same amount regardless of if you're at the North Pole or if you're at the equator. It's always going to be, what's the number? 69 degrees for 1 degree north-south. 69 miles, sorry. However, if you want to change your longitude 1 degree east or west, that depends on where you are on the sphere, right? If you're up near the North Pole, you can make a full circle around the North Pole in just a few dozen miles. But if you're at the equator, it's going to take you, 24,000 miles to go all the way around. So somehow, we are capturing the curvature of the sphere by the fact that the relationship between angles, which are how you measure distances on a sphere, and the actual distance traveled varies from place to place. So that's the idea here. We're going to have something in here, some array, that's going to tell us how the distances change with position. That's how we're going to capture curvature. And it's this metric tensor that's going to play the big role. Now, that's two-dimensional. The surface of the sphere is a two-dimensional thing. North, south, and east and west, 2 dimensions. What about spacetime? Oops. Spacetime has 4 dimensions. There's time, and then there's 3 directions of space. Now, if the spacetime is flat, it's a weird thing to think about, but if it's flat, what we mean is that it's basically like the geometry that you learned in high school with time attached, which means that a straight line is actually a straight line that you would draw on a sheet of paper. And so you'll see that there's 1s all along the diagonal. That's because it's just like regular flat geometry, nothing curved going on. There's also a minus c squared in the top right-hand corner. That's for reasons I will explain in a minute. But the point is if we want to describe a metric on spacetime, again, the metric tells us about curvature. That's the thing to keep together. Somehow we need to capture space and time in the same object without mixing them in the wrong way, which is kind of a mess, perhaps. So somebody clever, I think his name was Herman Minkowski, who's a Polish person. Sorry, no, he wasn't Polish. He was from Kaunas in Lithuania. Oh, where'd it go? Okay, great. Take a water interlude. Yeah, there you go. So one idea is that, well, we have positives and negatives, right? So maybe we make the positives be space and the negatives be time, and then we can kind of keep them separate that way. So instead of talking about distance covered, because we're talking about space and time, I'm going to use the word cost or interval. So how much does it cost to move through time? How much does it cost to move through space? It's the language I'm going to use. Also, sometimes we refer to the space-time interval. It'll be either positive or negative. That's the same thing as the cost. So we'll say that there's a positive cost to moving in space, and there's a negative cost to moving through time, just to keep them separate. And then you can imagine, Well, what if you were moving in space and moving in time? We all are. When you're walking around, you're moving through both. If you're moving through space and in time in exactly the right way, so that the cost of moving through time is the same, but negative, the cost of moving through space, maybe you'll get a zero cost. That's actually what light does. And if you work out the details, you can actually see that pretty explicitly. That's why the c squared is here. That's telling you that if you move at the speed of light, your cost is 0. So it's a particular type of path. It's called a null path. There's 3. There's space paths, time paths, null paths. That's just a little bit of a kind of diversion, but this is how we read off things about a space-time metric. The reason why we have positive ones along the diagonal in the space-time metric is because the cost to move in space is positive. We have a negative c squared because the cost to move in time is negative. You'll see that there's a little label here, g with the subscript tt, that tells you that it's in the time direction. Now, the question is how do we actually talk about a straight path in space-time? It's a little bit trickier because now we have positives and negatives. We can't just use the smallest thing. So instead we say that a straight path through time is the one that costs the most. A straight path through space is the one that costs the least. And this can actually give some intuition for this strange behavior of if you move fast enough, your clock slows down. And roughly it's because if what your clock shows you is the positive cost of moving through space and the negative cost of moving through time, well, if you're moving through space, the total cost will be, in some sense, less negative, right? Because you're moving through space a little bit, and that contributes positively to the cost. So your time on your watch will be less. That's one way that you can at least get time dilation out of this view of positives and negative costs. Now, the funny thing is, this is for flat spacetime. Everything so far, special relativity, no gravity at all. If you then say, well, what if we change the spacetime metric, like we did for the sphere? It wasn't just the same everywhere. Then that's changing paths in spacetime. And if you're super, super clever, you might come up with a way to change the spacetime metric so that the straight paths are circles around heavy things, and that would be gravity. So that was Einstein's intuition here. He wanted to figure out a way to describe gravity just using the geometry of spacetime itself. And so he wrote down this horrible equation. This is called the Einstein field equations. It's actually 10 coupled nonlinear partial differential equations, and this is my day job, basically. So on the left-hand side, you might see the letter G showing up every once in a while. That's the spacetime metric, right? This is telling you how to measure space, and then on the right-hand side, you have this capital T. We don't have to worry about all of what it's saying, but the right-hand side, that capital T, that tells you what the matter is doing. That tells you where is the matter, how fast is it moving, how dense is it. And so what this is saying is that the way the space-time metric changes, again, space-time metric tells you how to measure space and time, depends on where the matter is. So this is the idea that matter tells space-time how to curve. Then there's the relativistic kinematics. We're talking about relativity, of course. Kinematics is the path of things through space. So kinematics tells you how things move when there's no forces acting on them. So relativistic kinematics is just this idea that the matter, the way the matter is distributed, is controlled by the curvature of the spacetime, because it'll just flow along straight paths. And so you have an interrelation, which is very complicated. The matter tells spacetime how to curve, the spacetime curvature tells matter how to move, and somehow they're influencing each other. So you can imagine solving this equation to find that little g there, to find the spacetime metric, is really awful, incredibly awful, arguably one of the most awful things that you can do in physics, and yet it's something that I love to do. But one of the things about physicists, and not about mathematicians, by the way, no shame on mathematicians, but one of the things that physicists are really, really good at is taking something horrible and simplifying it dramatically by just adding a few assumptions. You may have heard of a spherical cow in a vacuum. It's an old physics joke. Cows aren't spherical. They also aren't in a vacuum. But, if you want to figure out how big a cow is, just to pretend it's a sphere, pretend it's in a vacuum, and now you can solve the problem, right? So what physicists are really good at is simplifying things, and people have done that to this, simplifying the Einstein field equations and come up with actual solutions to figure out what the space-time geometry actually looks like. And so our first example of that, we're done with math for now, is Karl Schwarzschild in 1916. I should say, by the way, Einstein had no idea about black holes when he was doing any of this. He hadn't even thought of it. In fact, Karl Schwarzschild hadn't either. But in 1916, Karl Schwarzschild published the first solution to Einstein's equations. Now, this is remarkable because if you know your history, World War I was being fought at the time. Einstein published his paper in 1915. He was in Switzerland. He was in Switzerland at the time. He wasn't yet anywhere else. He was in Switzerland at the time. Being neutral, he was probably fine. But Karl Schwarzschild was German. He was fighting at the time. He was literally fighting on the Eastern Front in World War I. He was an artillery guy, if I remember correctly. He was in his 40s as well. He volunteered to fight. You know, patriotism and all of this. This was a different time. And a few weeks after Einstein publishes his result, Karl Schwarzschild, he hears about it, and then he writes down a solution. Just a few weeks later, sends a letter to Einstein. Einstein's delighted, very, very impressed. He thought nobody would ever find solutions to his equations because they were so horrible. But he did, just a few weeks after the results, after Einstein published his paper, and then Schwarzschild published it. He sent it into a journal in February, I want to say, and he actually died later that year due to, I want to say, like tuberculosis or something. You know, that was the common way to go at the time. But his name, Schwarzschild, is basically going to be featured throughout this talk because even though he didn't know it at the time, the solution he wrote down was the first solution that describes a black hole. Now, at the time, this was just, you know, just some strange, weird solution to these equations. Nobody really understood what they were. But over the next few decades, you have people like Robert Oppenheimer of Oppenheimer fame, you know, the atomic bomb and all of that, and his student Hartland Snyder. They described gravitational collapse of stuff in space, or in general. And they showed that you would form one of these black hole objects. They weren't called that at the time. You would form one of these black hole objects inevitably if you had enough stuff. So Schwarzschild showed, well, there is a solution that follows Einstein's equations that looks like this black hole. And then Robert Oppenheimer and Hartland Snyder showed, oh, this can actually happen in the real universe. So it was at this point that, you know, this is the beginning of the golden age of general relativity, which I'll talk about in a minute, but I do have one more slide of math with a diagram on it. By the way, I'm going to skip Robert Oppenheimer's and Snyder's work because it's very, very complicated and involves a lot of complicated quantum mechanics. Schwarzschild's is just geometry, and I'm a geometry man myself. So the Schwarzschild solution, remember, a solution to the Einstein field equations just means a description of the space-time geometry. It's just what values do you put in this 4x4 array that solves that big, long, nasty equation. This diagram on the left is a diagram of that math over on the right. But the important point is that with that description, that captures all of the geometric features of this very nice black hole that Schwarzschild came up with. And so there are a few consequences. First, if you look at this equation, you can actually read off that there is a particular special distance away from the center of this black hole object. Namely, if you tried to shine a light beam out if you were 1 billion miles away from the center of this thing, the light would just go outward if you tried to shine it in the outward direction. But as you get closer and closer, what you'll find is that there's a very special distance that if you tried to shine a light beam outward, it would just never move further away from the center. It's kind of weird. Maybe that would be a black hole, right? A black hole would be something that, or perhaps you might call it a dark star, something that the light just can't escape the gravity. Another consequence is that if somebody was inside this Schwarzschild radius, that Schwarzschild radius is that special distance where light can't escape from, if you were inside and your friend was outside, you would never be able to send a signal to your friend outside. They could send a signal to you, but you'd never be able to send anything out to them. We call that special place, where you're that special distance away, we call that region the event horizon. It's the kind of the boundary of the black hole, if you will. And it's called an event horizon because a horizon is a place, or it's a region that separates two things, and it's an event horizon because points in spacetime are events. That's just the history of the name. Also, another strange feature is that, again, just from this formula, you can show that if you hang out near the edge of the event horizon of a black hole, your watch will slow down. If you're hanging out 2 millimeters away from this event horizon, and your friend is 1 billion miles away, their clock will tick way faster than yours will. You can figure out exactly how much faster. And then, if you're particularly observant, you'll notice that R is that distance away from the center. If R is 0, you're dividing by 0 an awful lot in this formula. And what you'll find is that if you were to go to the center of this thing, 0 distance away from the center, something horrible must happen because you can't divide by 0, right? And so you get something called a singularity. That would be at this center of the black hole. I'm going to skip this next bit. But The important point is that all of the geometry of the black hole, the simplest ideal black hole, is right there in this 4x4 array. Now, there's a lot to be said about it. It's been studied for 100 years, but there's a lot to be said. Anyway, by the end of the 40s, leading on to the 50s and 60s, we have what's called the Golden Age of Relativity. Now, we have a few famous people here. You might recognize some of them, particularly probably this guy. But starting in 1963, we have Roy Kerr. Roy Kerr was perhaps the second person to come up with the solution to Einstein's field equations. Not actually the second, but maybe the second important solution. He came up with a description of a rotating black hole. Then we have Ezra Newman in 1965, who came up with the description of a rotating and electrically charged black hole. And then in the same year, we have Roger Penrose, who won a Nobel Prize a few years ago for his work showing that even if you have some horrible arrangement of matter, inevitably it'll collapse to form a black hole. So these are things that will actually form. I should clarify, by the way, that the work of Oppenheimer and Snyder, they required that their system is like perfectly spherical, and then it would collapse to form a black hole. Penrose showed that it doesn't have to be perfectly spherical. It can be any horrible arrangement of anything, and you'll get a black hole inevitably. And he won a Nobel Prize like 5 years ago for that, for basically theoretically showing that black holes are real. And then, of course, there's Stephen Hawking. In 1970, he wrote down this thing about, or he started describing something called black hole thermodynamics, which is a big deal. I'm not going to go into the details there, but that's the first thing that he got super famous for. And then he also came up with this thing that we now call Hawking radiation, which I mentioned a big asterisk at the beginning, namely that black holes aren't actually perfectly black. They do leak a little bit of energy, and that was because of Stephen Hawking. He showed that this is a thing that really happens. Theoretically, right? It's hard to see this. But so those are like the kind of four huge names, and during this period of the 1960s, 1970s, we also got our first hint of a real black hole in space. This is in 1964. There was the way that we measured X-rays in space is you would send a rocket up, you would have something spinning on it, so it could basically sweep over the sky and then look for flashes of X-rays. And so that's what they did in 1964, and they saw this really bright X-ray source in the sky in the Cygnus constellation. And nobody really had a good explanation as to why there was this super bright X-ray source in space. But some people thought, well, if something was to fall into a black hole, it would get really, really hot. And we know that the hotter things get, kind of the bluer the light they emit gets. Think of like a hot lump of iron, it's red. If you get it hotter, it gets yellow, then white. If you get it even hotter, it'll start glowing in ultraviolet. If you get it even hotter still, it'll start glowing in X-rays. So the thinking is that, well, stuff falls into a black hole, gets really, really hot because there's a lot of friction. Maybe that would explain why you have this bright X-ray source that doesn't emit any other light on its own. It wasn't emitting visible light that we could see. So maybe it was a black hole. Later, it was found that there was a big heavy star orbiting this thing that was emitting X-rays. Nobody knew why, unless it was a black hole. And so maybe that big heavy star was having its matter sucked into the black hole, providing the matter necessary to make it glow. So by the mid-70s, it was basically agreed by everybody that, yeah, this is a black hole. It was the first one that we ever saw. Very indirect, though. Then in the 90s, we started taking better data about the center of our own galaxy. If you don't know, we now know that there's a black hole at the center. But at the time, they didn't know. What they saw was a bunch of stars orbiting something they couldn't see. And they were orbiting really, really fast. Those stars at the center, the fastest one, is moving 8% the speed of light, which, again, to put this in perspective, is 24,000 kilometers per second. That's going all the way around the Earth once a second. So these stars are moving wildly fast around something that they couldn't see. It must be a black hole, right? Fast forward again 20 years, we have, you may have seen GIFs like this, we found gravitational waves. This was a huge deal, at least for me. I remember actually the room I was in when I heard the news. I was in grad school at the time. Basically, going back as far as the 30s, Albert Einstein predicted that if you have stuff moving around in spacetime, it'll cause spacetime to ripple a little bit. And he thought, well, maybe these would be eventually detectable, but not with the tech they had at the time. And then, actually, a few years later, he retracted that claim, saying, oh, no, that was wrong. And then a few months later, he actually retracted the retraction. He said, oh, no, it was actually right. But now we know that it was right, and we detected them for the first time in 2016 with the LIGO instrument. And it turns out that the best way that we could explain that particular ripples in spacetime that we detected was if two black holes had collided. There's no other explanation for how we could get that much ripple in spacetime, if you will. So again, another indirect observation that black holes are real things, but so far it had only been indirect. Until 2019 and 2022, we actually got our first, in some sense, direct observations of black holes. The one on the left is the black hole at the center of the M87 galaxy. That one's enormous, and it's also millions or maybe even billions of light years away. I don't know the number off the top of my head. The one on the right is the black hole at the center of our own galaxy, Sagittarius A star, so called because it's in the Sagittarius constellation in the sky. And what we're seeing here is you're seeing the glowing stuff around the black hole that gets really, really hot as it falls in. Now, you can't see anything in the middle here, because that's where the black hole is. Of course you can't see the black hole. It's supposed to be black. So yeah, there's going to be a shadow there, and that's basically where the event horizon of the black hole is. We were able to resolve it. Now, keep in mind, black holes are very, very dense. So even though these things weigh millions of times the weight of the sun, these things are the size, at least ours, is like the size of the orbit of Mercury or something like this. So it's fairly small on a galactic scale. M87 star is much, much bigger, but it's also much further away. So we now have direct observational evidence that surely black holes exist, stuff falls in, and basically all of the math coming from Albert Einstein and Karl Schwarzschild and Roy Kerr and so on, all of that math, there was nothing wrong with it. It was all perfectly good 100 years before this was ever observed. So that's incredible, but that brings us up to modern day. We are now, this picture was 2022, in May in particular. And the way that they did this is a fascinating story. I don't have a whole lot of time, so I shouldn't tell the story. But basically, they made the entire Earth a telescope, which is a huge feat of engineering, a huge feat of science. But anyway, so the question is, well, all of the questions are big. So I went over like the very basics of the black hole stuff, but there's so much more that we now have to ask. In some sense, it would be nicer if black holes didn't exist, because then we'd understand the world a lot more. But because they do exist, it gives people like me stuff to do, right? So there's questions that we have, like what's the deal with time? So I said at the singularity, time stops. I have no idea what that could mean. I have no intuition for what that is. But even stranger still, even if you're not at the singularity, time and space swap order. They swap places inside a black hole. You usually think of being only able to move forward in time and move around however you want in space. Within a black hole, you can move whatever direction you want in time, forward or backward, but you can only move inward. So space becomes time, time becomes space. What's the deal with that? I don't know. It's what the math says, and it works, but it's very weird, and it makes us ask what time even is. Then there's questions about space. What's space doing? So I mentioned these laws of black hole thermodynamics that Hawking kind of started in the 70s. One of the ways that we can talk about them is talk about entropy. Entropy is like a thermodynamic thing. You may have heard of it. And typically, it's a number that tells you how disorderly a thing is. And if you have more of the stuff, if you double the size of the thing, you usually expect the entropy to double as well. The strange thing about black holes, as Hawking showed, is that, Hawking and Jacob Bekenstein, is that it actually scales not as the volume, not as the volume of the black hole, but as the surface area of the black hole, which is very weird. And as a result of that, people started to think, well, maybe that third dimension of space, not actually real. Maybe our universe really is two-dimensional. This is the idea behind holography, which you may have heard about if you read science stuff ever, which is just the idea that space itself might emerge from quantum mechanics somehow. And that idea originated with this thought about what's going on with black holes, black hole entropy in particular. And then, of course, there's the big daddy question of all, what's the deal with gravity at a quantum scale? Now, this is probably, in my view, the most important question that we have right now as physicists. Penrose's Nobel Prize was for showing that you'll always get collapse to a singularity, but he didn't include any quantum mechanics. And quantum mechanics is the physics of the very small, and singularities are very small. So the question is, well, if he didn't include the physics of the very small in his calculation of something very small, was it really right? So we need to somehow understand what gravity is doing at the very, very microscopic level, and nobody has any idea how to do this. People have been trying. In fact, Einstein tried back in the 50s before he died. We've made progress, but nobody has any idea how to do it. Maybe quantum gravity, a theory of quantum gravity, will explain what the singularity is. Maybe it will somehow explain what time's doing, what space is doing. And black holes are kind of the ultimate test bed for anything quantum gravity, because we know they exist and we know that they must involve quantum gravity. So if we figure out this, maybe we'll have an answer to the 2 previous slides. And so anyway, the question then is, so what? Well, look, maybe you don't care about quantum gravity, maybe you don't care about black holes at all, but there's at least a reason you should care about black holes, because if you can understand black holes, you can understand quantum gravity. And if you can understand quantum gravity, then you can answer questions like, where did the universe come from? Did the universe have a beginning? Where will it end? What is space? What is time? These are all really deep, kind of almost philosophical questions that one would hope, if we can understand black holes, we can understand those questions. So I wrote down a quote that I should read as a concluding remark. If you've ever wondered where everything came from, you should look in a black hole first. And that's all I have to say. Hopefully now you care.
So we do have time for questions. If you have questions, please raise your hand. Reminder, ask one question relevant to the topic, and then we'll move on to the next person. If you have a follow-up question, we'll come back around to you, but please only one question at a time.
Thank you very much. Thank you so much. It was so interesting. I really appreciate all the information that you provided to us. So you mentioned Hawking radiation at some point during the discussion today, and my question is, does this Hawking radiation, if it exists, does it mean that the information that you throw to the black hole survives somehow? And if so, then what kind of information are we talking about? You mentioned several books in the beginning, like if you throw one of those books in the black hole. So, yeah, thank you.
It's funny, that is probably the hardest question that we've known to ask since like the 80s. And there was a famous bet. The question is about the black hole information paradox. You throw information in, can you reconstruct it out from this information or from this energy that leaks out of the black hole? Generally, it's agreed upon that, yeah, you probably can reconstruct it if you are really, really precise and you measure this radiation. But nobody really there's not really agreement as to how it works. This is an open question. I should say this is one of those cases where like the answer is probably yes, but we don't know why. There's a lot of disagreement as to how exactly it works. So I don't know.
Question. What did you think about Interstellar? Not so much the time travel stuff, but the depiction of the black hole, the swirling, and of course the gravity, the time displacement issue.
So I was actually recommended to see that movie by the professor who's actually at ASU, who taught me general relativity. He came into class, this was in 2015 is when it came, 2015 when it came out. And he said, yeah, you guys should go see this movie, it's really good. And I did, and I thought it was great. Generally, the science is really good up until the last 15 minutes where they go into the black hole and then there's like a bookcase or something. Besides that, it's all really good. The depictions are excellent. They actually published a paper on how they did the the simulations to generate the images. So yeah, I'm thoroughly impressed. Yeah. Yep. And then some computer scientist, I think, played a role. Yeah, really liked it.
Yes, I'm sorry. My question is this. Light, as we use it on solar cells, which we have all over this building, is a particle. Light in the electromagnetic spectrum is a wave. What is it?
Yeah, so I have I perhaps take a heterodox position here. I think that light is always a wave. The way that I think about it, it's definitely always a wave, but sometimes it's a wave with particle-like characteristics. There's a word that somebody coined. It's wavical, which is kind of cute. But yeah, I mean, the way that at the very fundamental level, the way that we describe things like light or things like electrons or whatever, it's always a wave description. And then sometimes that wave is like a wave packet, in which case it behaves like a particle would. So, I mean, generally speaking, fundamentally, my answer is it's definitely a wave, but sometimes it's a wave that behaves like particles.
Is this a fair question? What is a white hole?
Yeah, so it is a fair question. So a white hole, so the question is what is a white hole, right? The idea behind a white hole is that generally the equations that we use, the Einstein field equations, they work backwards and forwards in time. Like you can basically flip, like if you were to draw a diagram, you could flip the whole diagram around so that time runs backwards instead of forwards, or equivalently you can think of everything kind of running in reverse, and then you would end up with a white hole, a thing that only emits stuff and nothing can fall in. Now, it's like a theoretically interesting idea. As far as I know, there's no known mechanism as to how such a thing would form, and if they existed in the universe, we would definitely see them, because they would be wildly bright, right? I mean, rather than things falling in, they would just be emitting stuff all the time. And so, probably don't exist, probably just a kind of like a hypothetical theoretical construction, but it's definitely something we're thinking about.
Your belief that everything is a quantum wave, and there are other physicists like Feynman that say definitely light is a particle. He was very adamant about that. It's a particle, it follows all paths, you know, and then you mathematically add them up. It was, Feynman diagrams show all forces as being particle exchanges. Does it make any difference?
Yeah, so in some sense, so we're talking about quantum field theory here, which is, you know, complicated, but quantum field theory is a theory about measurements, right? You set up some experiment, and then you make a measurement, and you detect something. Maybe you detect a little tick on your detector of some kind, your photon detector, whatever it might be. And so regardless of the viewpoint that you take, if you take Feynman's view where everything is a particle that takes all possible paths and then things are well described by Feynman diagrams, or if you take the view that these are quantum waves that are kind of overlapping and interfering with each other, you get the same answers. And so the question of like what actually is matter is a question probably best left to the philosophers. You know, I have my own opinions on the matter, but like instrumentally, just from the things that we measure, there's no difference.
As a science interpreter, I'm sure you're familiar with how lots of people like to use unanswered questions in science, the mysteries that we still have in science, kind of as fodder to support their own ideas, supernaturalist ideas, conspiracy theories, etc. What's your approach to, because you're on social media quite a lot, what's your approach to dealing with arguments from ignorance?
So, it depends on the context. You know, if I'm having a conversation with somebody, if they're receptive to learning, I'm happy to like switch into teacher mode, right? You know what you learn in grad school is to lecture to 150 grad students or 150 undergrads or something. I'm happy to switch to that. Be like, hey, here's the experiments. Here's what we know. Here's what we don't know. If you don't know something, then you don't know it, and that's okay. On the other hand, there are people who are very, very, they have some preconceived notion about, I don't know, telepathy, or not telepathy, telekinesis or something. They're like, telekinesis is real. I've heard of that quantum mechanics thing. Quantum mechanics explains it. So those people, they often don't want to talk, and so it's better to just explain why they're wrong and then show them what things are right. The way that I've typically done it is I take the opportunity of somebody who's doing that kind of thing, talking about something that's obviously nonsense. They're not going to listen, but somebody else might, and if they listen, then I can teach them some cool science in the meantime. So there's not much to do otherwise.
You seem very interested in cultivating an attitude of curiosity and genuine interest in physics. I wonder, have you heard of or played the video game Outer Wilds?
I've heard of it. I haven't played it. Anybody who knows me, my mother and my wife will both definitely know this, that sometimes it's very, very easy to throw yourself into something and get lost in it. There was a game called Factorio. I don't know if you've heard of it. That game is like, well, it's like something I probably can't describe, but essentially I lost a summer to that game, so I tend to not go into those games that I know I will definitely lose myself in.
Thank you for a wonderful, interesting talk. Sort of two-part question here. Aren't there black holes at the middle of every galaxy? And if so, don't black holes, aren't they always growing and bringing in material, eventually won't they absorb all that material in that galaxy?
So it's a good question. Generally, almost all galaxies will have black holes in them. There are some, I think that there have been some that have even been detected, or at least we've inferred that there's no black hole. And the idea is maybe it got lost, maybe it got kicked out by some, like, maybe it swung towards another galaxy and it kicked out their black hole or something like that. One of the ideas is that probably there's a relationship between how the black hole formed and how the galaxy formed to begin with. At least for large galaxies, there's like a bunch of little baby ones that don't have them. But that does bring up an interesting question as to, well, if the black hole's there, why isn't everything falling into it? And it's actually kind of a misconception that black holes are any more dangerous, per se, than like a big star. And the reason is because black holes are just gravitational objects. Things will orbit them, no problem. If you get too close, you'll definitely fall in. But most of the stuff, I mean, the stars that I showed, the animation that I showed here, most of these stars are going to continue orbiting for millions, or perhaps, well, depends on how long they live, but they'll orbit for millions of years because it's just a gravitational orbit. Now, they might get flung out by some other gravitational thing, or they might get accidentally like pushed in by some other gravitational thing, but generally they're pretty safe to be around as long as you're not too close. There is something to be said, though, that if you project to the long future, the idea is that, yeah, eventually all of the stuff in a galaxy will coalesce into a black hole at the center, if only because orbits eventually do decay via gravitational waves, actually. And so you would expect that they would lose energy very, very slowly over trillions of years.
Thanks again, Dr. Blitz. Forgive me, this sounds like an ignorant question, but I've thought about this for a long time, and I wonder about this, and perhaps a lot of people do too. So as you know, Lawrence Krauss wrote a book, A Universe from Nothing. And I think, you probably know, and most people do, that he talks about nothing in a different sense that like philosophers do and stuff. But I've also heard Daniel Linford, PhD in philosophy of physics, talk about the potential for the origin of the universe happening from like something called sans, or without metric time. So my question is, in your view, does it even make sense to talk about something like something from nothing, quote unquote, or the universe deriving from something without metric time at all?
So there is a geometric notion of time called affine time, which, well, okay, so metric time is what a clock does, right? There's affine time, which is kind of just what a clock does, but arbitrarily rescaled. So there's not really a notion of units of time, but there's definitely a notion of past and future. This is closely related to conformal time, but there is a way that you can make sense of universes without a metric, without something that describes how much time has passed. I don't know how to make sense of things personally. This is a personal failing. I don't know how to make sense of things that don't even have any notion of like past and future if there's something that's supposed to happen. But that said, the notion of temporal emergence, the emergence of time from something more fundamental, is something that's talked about, and it's just very confusing. I don't know if anybody has any good intuition for it. But yeah, maybe, but we'll need quantum gravity for that.
Hi, excuse me. Hey, I have a question. I have a time measuring device here, and in my car I have a little device that connects with my phone and tattles on me. It somehow tracks my velocity and my acceleration in my car. And I'm just wondering, are these sort of along the lines of a time-space sensor? Is there something that directly can output what a thing is doing in time-space without having to go through a big computer?
Well, okay, so definitely a watch is a temporal measurement device, and a speedometer perhaps, or like an odometer or something, is definitely a spatial measuring device. And so you can definitely measure things like durations and distances, no problem, super easy to do. The trouble with measuring space-time curvature is much harder. So the canonical way that we measure space-time curvature today, like out in space, if the universe is curved, which it is ever so slightly perhaps, is you have to basically draw giant triangles. In fact, you can imagine drawing a triangle on the surface of a globe, connect one piece at the North Pole, and then two more legs down on the equator. That would be a triangle. All the lines would be straight. It would have three sides. But if you add up the angles on the inside, you get more than 180 degrees. And that's because of the curvature. So one of the ways that you can measure curvature, if you actually want to measure space-time curvature, is by basically drawing or imagining triangles in space-time and computing angles. Otherwise, it's very, very hard because gravity is very weak, so space-time curvature is very small, generally. So you need to use really, really big things. Or you can use very, very precise things, neither of which a watch or an odometer is. Sorry, one more thing. You actually can measure the gravitational time dilation with very precise clocks on Earth. Earth has gravity, so time flows more slowly at the surface than it does higher up. If you get an atomic clock, you can put it on a table, and then you can lift it up by a foot, and you'll measure a very, very tiny difference in the rate at which it ticks.
So Aaron thought his question was ignorant. Mine's probably going to be considerably more. But I've seen some headlines lately, and are we in a black hole?
No. Okay, I should back up. Excellent question. I've definitely answered that question like 40 times in the last week, probably, because I do like online Q&As twice a week, and so I get that question every single time. So there's this idea that we were in a black hole. The idea comes about from a physicist named Pathria in 1972. And so he basically observed, hey, look, the size of our universe kind of matches the size that a black hole should be if you account for all of the matter in our universe. And that was great idea, except he didn't know that the universe's expansion was accelerating, which kind of throws that whole idea out of the water. So that idea from the 70s, brilliant idea at the time, has been dead ever since the 90s, basically. Then what happened, and if you read science, pop science news or whatever, you may have seen news articles popping up in June or something like this. Scientist discovers we're in a rotating black hole or something like this. So what happened is that, I want to say it was in June, a computer scientist named Lior Shamir published a data analysis paper, that's his expertise, where he analyzed the rotation rates of galaxies. And he found that more galaxies are rotating one way than the other, which is kind of weird. We would expect it to be 50-50. And so in the discussion, long answer, the only reason I know the answer is because I had to do debunks on this. In the discussion article of that paper, he gives like 6 possible explanations, one of which is, maybe we're in a black hole. And so news headlines have grabbed onto that and said, scientist says we're in a black hole. Now there's an even deeper problem, namely, nobody's actually computed what it would be like to be inside, what it would look like from inside a rotating black hole. Nobody's done that math. So if we're interested in doing science properly, where you have an observation, you make a hypothesis, and then you check your hypothesis against the data, somebody's made an observation, galaxies are spinning differently, but there's no hypothesis yet. There's nothing that can make a prediction because nobody's worked out the math, and the math is atrociously hard. So we're definitely not even at the is there evidence stage because we don't even know what the question we're asking is.
One more question that I've been seeing online a lot recently is this idea that time is actually not real, right? It's not a thing. So for those of us who are not physicists, most of us aren't, first of all, like, what is that position? I'm sure you know it, and then what is your thoughts of it?
Yeah, so this is a philosophy question, right? Like, is space real? Like, kind of seems real, but then the question is what is it? You could take the position that time isn't real, only durations are, only things that you measure, like what a clock does. But then you could also say, well, space isn't real either. It's just what you measure, distances. So the position is basically that time is not some thing. It's not some fundamental object. Rather, it's just like kind of a human accounting of what clocks do, which is a fair point to make, especially if it's an emergent thing. We wouldn't say that, like, wetness of like a cup of water is real. We would say that like a thing being wet is just like what H2O molecules do when they do certain things. So maybe there's some sense to it. I'm on the fence. I don't know. Maybe time is, anything you say about time you should say about space, certainly. So maybe space-time is fundamental. Maybe there's something there. Or maybe it's not, and it's just some more emergent from something more fundamental. I don't know.
Hi, love your talk. I actually have a series of questions. Hopefully they're short, and it'll kind of tell me which way to go. But do you believe in quantum space?
Quantum space.
Or space that is purely a void. There's nothing there.
Oh, yeah, so not quite this picture, but closely related. So yeah, so there is this idea that Even if you sucked all of the atoms out of a volume of space, there will still be something there. We would call those quantum fields. And those are, they kind of have to be there, otherwise our whole description of the universe is just wrong. So yes.
Do you believe everything is made of quantums?
Probably.
And do you believe in the fractalness of the universe?
I don't know exactly what that means. I know what fractals are. So at the base layer, quantum fields are just like, think of it as like a way of describing a measurement at every point in space-time. So you could imagine that like the temperature at this place in space is, I don't know, 78 degrees, and the temperature over here is 76 degrees, and you could describe that for every moment of space, every moment of time. And so a quantum field is just that, but more complicated. So if there is a baseline, if there is fundamental quantum stuff like electrons and photons and quarks and all of these, then it seems like that's like the bottom, and so there wouldn't be any like kind of fractal kind of self-similarity lower. I am inclined to think that there should be a bottom. I don't know what it is.
Okay, so this question I hope will be an easy one. This is about the event horizon and point of no return. If they are always at the same place for all objects, like when you're talking about light, about photons, they fly with no mass into the black hole, and obviously their point of no return is the event horizon. When we're talking about like an astronaut or any body with significant mass, then will that point of no return be further from the event horizon if I have some really powerful something that pulls me out? Spaceship, yeah.
So, I mean, it's a good question, certainly. We generally define, I mean, in some sense, the mathematical answer is yes, they are identical. And the reason for that is simply because, in principle, an astronaut, if you had a strong enough rocket, could go arbitrarily close to the speed of light. You could never get there, but you could get really, really close, so much so that if you were even a millimeter away from this point, you would eventually escape once you got fast enough. At that point, you would, so the only difference is that at that point, a light beam can stay stuck there. An astronaut could never stay stuck there. But there's never a place where an astronaut must stay stuck. Yeah, if you touch it, either you're losing your finger or you're losing your whole person.
Another question. Are scientists currently or have tried to create miniature black holes?
So it's a good question because this was a thought that the Large Hadron Collider in Switzerland might do it before they turned it on. I think it turned on in like 2008 or something. So at the moment, I'm sure that there are people who are trying to do this, but at the moment, nobody seriously believes that it's possible with our current tech, if only because the energy required to do so, it's really easy to just make like a gas cloud, right? But to actually make that gas cloud compress enough requires obscene amounts of energy. And I mean, consider this, the energy that's involved in smashing protons together in Switzerland requires a particle collider that is, 26 kilometers across or something like this. If you wanted to do the same thing to smash protons together to form a black hole, it would have to be the size of the solar system. So unless somebody can come up with something like way more efficient, and there are people working on this, but it's in the infancy, then no, there's not really any hope of doing this right now. Although it would be great, because then we could actually study these things very directly.
My question is, every now and then there's this little theory being kicked around that we're all living in a hologram and that there is no reality. And then you try to, either defend it or reject it. But what is your feeling about that?
So there's kind of two notions that some people posit. There's like the simulation idea. I think the simulation idea is kind of silly, but that's just me. But the idea of holography, this idea that really our world isn't three-dimensional, that we're like living, that we're actually two-dimensional things that have this illusion of three-dimensional reality, that's a real thing that people take seriously. My position on the idea is that at the end of the day, it's philosophical as to what that actually means. The actual mechanism of holography is just that there's two equally good ways to describe reality. Maybe one equally good way to describe reality is a three-dimensional space, one dimension of time, universe with gravity, On the other hand, maybe another way to equally well describe reality is 2 dimensions of space, 1 dimension of time, and no gravity. And if they're 2 equally good descriptions, then in some sense they're describing the same thing. And so I wouldn't go as far as to say that if the holographic principle is true, that means that, you know, our reality is an illusion. I would just interpret it to mean that, well, whatever our reality is, it's something deeper than either of them, because there's 2 kind of different descriptions of the same thing.
Do we have any further questions, or are we all thoroughly stunned here?
So I've heard that there are possibly a lot of like small black holes flying all around, including in our galaxy, that we cannot probably observe, but they are flying somewhere. And theoretically, there is a very small, tiny opportunity that a small, tiny black hole will fly through me, for example, in the next minute. And what will happen to me if that happens? How exactly will I die? Will I just like disappear and get sucked into that little black hole completely, and then our police will be wondering what happened to me? Or is it going to be a different scenario?
It's an excellent question, and surprising absolutely nobody. Physicists have asked that question and written papers about it. So just for context here, the idea is, you may have heard of this thing called dark matter. The idea is that maybe there are just tiny black holes everywhere, and that's what dark matter is, because you can't see black holes, they're dark. And so if it's the case that there's just tiny black holes everywhere, they would be called primordial black holes, well, then maybe if they're flying around, then one could just pass right through a person. Now, in fact, so yes, it would absolutely, well, okay, I should back up. So they can't be smaller than a certain size, because if they did, via this thing that Hawking did, they would be gone by now. If they were created, if they formed in the very early universe, they would have evaporated away. So they have to be bigger than a certain size, and I think that like currently the lower limit on size is like the size of a small asteroid, not volume, but mass. And the upper limit is something like, otherwise we would have seen them as something like the size of the moon or something like this, if I'm remembering correctly. So there's a range over which the size can be. Now, the question then is, if they were on this, if they were somewhere falling between, you know, those 2 mass ranges, what would happen if one of them hit you? Well, it would be fatal, definitely fatal, because, you know, it would be like getting shot with a particle beam, basically. This is a divergence, but there was a story of a guy who accidentally turned on a particle collider with his head in the way. He survived, but like it wasn't pretty. So that's basically what would happen to you if it passes through an important part of your brain or your heart. You'd probably have a bad time. You wouldn't get sucked in; it'd just be like a particle beam. But it wouldn't be pretty. But the important point is that a colleague of mine actually wrote a paper about what we can know about the prevalence of these black holes by supposing the fact that this has never happened in human history, right? Because if it had, we'd probably know about it, or at least one would think that there'd be stories about something like this. And so the idea is that if it's never happened in human history, they must be rarer than a certain amount, and therefore to account for the dark energy or the dark matter, they have to be heavier than a certain amount. So basically, he used the fact that this has probably never happened to kind of constrain how big these black holes can be, which is cool, but also maybe it just hasn't happened yet, and then it'll be fatal, and no one would have a good time.
So we have one final question. It'll be the final question for the day, and then we'll do our wrap-up. We have a question from online. We are being asked, how do black holes grow? Do they primarily consume gas and dust, or do they also merge with other black holes?
So most black holes will grow fairly slowly in relative terms by just consuming the things around them. Most black holes in the universe form from a star exploding, a very, very heavy star, and most stars are hanging out near lots of dust and gas. Sometimes there's partner stars as well, and so they'll just eat those things and grow very slowly. On the other hand, we do know that black holes tend to merge with each other a lot, and that's another way to very quickly grow the size of your black hole. The one that I showed earlier, this black hole collision, you had 2 black holes. I want to say that one was like 60 times the mass of the sun and one was 30 or something. And so you ended up with something that was slightly less than the sum of the 2 masses. The rest of that energy was released in the form of gravitational waves. So yeah, it's both, basically.
Fantastic. Well, I wanted to say thank you so much for an excellent Very informative and very entertaining talk today. Thank you so much. As we wrap up, I'd like to give you an opportunity to plug your own socials, your own ways of getting out there to the world.
Yeah, so if you search my last name and then slap on PhD at the end on Google, you'll find me. It's my account on TikTok is Blitz PhD. My account on YouTube is Blitz PhD. My account on Instagram or wherever, it's all the same. So if you want to see either debunking content, which some people like, or debate content, which other people like, or just science content, which other people like, go there.
Fantastic. Thank you once again for an amazing, amazing talk. So,